Hello. Hello, sir. Hello. Hello.
এখানে তো কোনো অডিও পোর্ট দেওয়া নেই যে এখান থেকে যে তাহলে এটা খুলে দিতে হবে নিশ্চয়, তবে ওটা এবারে পাবেন না। না না ঠিক আছে,
ওটা অফই করে দাও না থাকবে। হ্যাঁ থাক, ই হবে নাকি ভাইব্রেট হবে যদি সাউন্ড। স্যার ফোন ফোন করে শুনতে পাচ্ছি কিন্তু।
একটু আগে তো কথা বললেন স্যার,
ওটা তো এতে শুনতে পেয়েছি, এতে। হ্যাঁ, আমাকে কি শুনতে পাচ্ছেন এতে? না না, ফোনে নয়, ইয়েতে টিমসে শুনতে। আচ্ছা, টিমে শুনতে পাচ্ছেন? আচ্ছা ঠিক আছে, ওকে। হ্যাঁ
শোনা যাচ্ছে? ঠিক আছে, শুরু করবেন। হসপিটালে তোমার কখন না
Okay, all of your attention, please. So your next experiment is what? Your next experiment is given to you, that is on in Verilog, isn't it? So you have to using Verilog. You have to write the program, and you have to simulate, isn't it? So before going to Verilog, first of all, I will show you how to. I think all of you have installed your iVerilog. Huh? All of you installed iVerilog in your machine? Okay. So okay, even though I will just tell you the steps how to install iVerilog in your machine. First of all, what you have to do? See, these are the command already it is given. Okay, how to install your iVerilog in your machine. Okay, the commands are given, and the file is also, I think, Sir is given the file. So this is the iVerilog. Okay, iVerilog download for Linux. So from here you can download the file in your machine. Then after that you have to install it. So for installation, the process is also given. The process is that what? So you have to write some command on your terminal. Okay. So first of all, you will update, write sudo this instruction. then you have to write sudo this install iVerilog. So once you write this one, your iVerilog will be installed in your machine. Okay. So after that also you have to install your GTK web. Okay. So just that is used to view the simulation. So for that installation, you have to write this command sudo this one install GTK web. Okay. So only this 3 instructions is needed to install the iVerilog and this GTK web. Okay. First you will write the update, this update, then iVerilog installation, then GTK web installation. Okay. Only with this instruction, 3 instruction, you can download the or you can install the iVerilog in your machine. So once it is been installed, now you have to write the program. Okay. So for writing the program, just I will discuss some point about the Verilog. Okay. So already I think Sarah started the Verilog, isn't it? So just I will. Oh, it's not started. So I will just give you the concept about the Verilog. Okay. What is Verilog? How to write the program in Verilog. Okay. So basically, when there are 2 types of this high definition languages available. One is VSDL and another is a Verilog. Okay. But in our lab, we are using the Verilog. Why? Because there is some advantage of using Verilog than VSDL. Okay. So the basic concept of the Verilog module is what? That is, in Verilog, the basic unit, the hardware which we are going to write, that is called a module. Okay. So the basic unit of hardware, because this is basically what you are doing, some sort of circuit. Okay. So that circuit you're just expressing, means your hardware circuit you're expressing in some language. Okay. So that is why it is called hardware definition language. Okay. So here basically each and every unit, the basic unit is called a module. So in this module, the modules contain definition of a other module. That means in one module, you cannot write the other module definition. Okay. Suppose you are writing a program for a D flip-flop or any counter. So you cannot write the other definition. Okay. Suppose you are writing a counter, you cannot write inside the D flip-flop. So yes, you can do. That is called a instantiation. That we will see what you can do. In modules, cannot contain definition of other modules. A module can, however, be instantiated within another module. Just I have told you that you can instantiate, but you cannot write another module definition inside the one module. And this Verilog module, it allows the creation of a hierarchy. Okay, that we will see how. Now, this is the basic syntax of writing any module. Okay, so just you can see the SAR which has given some example. Okay, here you can see the module FA structure ABC. This is a program SAR has given to you, isn't it? Full ladder circuit. This is a full ladder circuit. So here you can see, just we are discussing first module, then you have to give the module name, then inside you have to give the list of ports. You can see the SAR has already given module, a module name, and inside the port, which port you are using, means input output port. Okay. So now you have to declare the input output declaration. Okay, that means the port which you are using, suppose I am using port A, B, C, or some output port. So that you have to here declare. My A, B input is my input port and out is my output port. So that way you have to declare here. So in this program, you can see that SAR has given the declared input A, B, C in are my input and output is my C out and sum. Okay, so this is a full ladder circuit. For full ladder circuit, you know how many input is required? 3 input. So ABC has been taken as a 3 input, ABC in, and 2 output. That is a sum and carry. Okay, so it is declared input ABC in and output as C out and sum. Okay. So input output declaration. Now some local net declaration. That means when you are drawing, if you draw a circuit, okay, this full adder circuit, you will find that internally some connection will be there. That means from one gate to another gate, there will be some connection. So that also you have to define here. Okay, so that is called a local net declaration. Okay, suppose in this example you can see in this local net declaration here wire W1, W2, W3, W4. So these are basically a local net declaration. Okay. Now there will be some parallel statements. Okay, some assign statement or some statements will be there, and here you have to write the end module. So this is how your basic syntax of any type of module. Okay, so when you will write the module, at that time you have to follow this syntax. Okay, first module, then module name, then whatever the port you are using, all the list of ports, then your input output declaration, some local net declaration, then some statements will be there, and end module. Okay. So this is the basic syntax for any type of Verilog module. So this is some simple example of an AND gate. Okay, so you can see the module name, it is given F, X and Y. I have taken X and Y as my input, output is F. Now this is my statement. Okay, assign F equal to X and Y. So this is a statement. Okay. End module, then end module. So this is one example for a two-level circuit. You can see that module A, B, C, D, F, then input, output I have declared, wire, okay, local net declaration, then I have assigned some function, then end module. Okay, now here the basically when you are instantiating any module, okay, so that time you can specify using these two methods. One is called positional association and another is explicit association. So this is basically highly recommended. Why? Because if you go by positional association, that means in your main module, if you have written like this, suppose add, then I have written in my add, I have given some name, then I have written, suppose this is my out, then this is my out, then input, A, B, C, in. So when you are going to instantiate the module in your inside the module, that time you have to, if you follow the positional association, then you have to write in the same pattern. That means there's output will be there, then again output, then input. So you have to follow that pattern. Suppose if your declaration is very lengthy, okay, then what you have to do? You have to follow in the same way. That means first I have written my C out. So in your declaration, there also you have to first declare the C out, then sum, then A, B, C, like this. Okay, but sometimes this may occur very problem, isn't it? Because you always have to remember in which pattern you have written in your main module. Okay, so basically this is highly recommended. Why? Here you can list in any order. Means you don't have to follow any order. Okay, that's just what you have to do. You have to give some name just to link with your main module variable. Okay, suppose for .in1 is my linked with my A input of the main module. Here my .in2 is linked with the main module with the variable B. Just like this. That means here you don't have to follow any order. There's no required to follow any order. You can write randomly. Okay. But if you go in a positional association, that time you have to follow the order in which you have declared in your main module. Okay.
This is for instantiation or
yes. No, for instantiation. Okay. So we'll see the example. Okay. So there are two type of variables, data type variable. One is called net and another is called register. Okay. So these two data types, you can see the net is must be continuously driven. Net type is must be continuously driven and used to model connection between continuous assignment and instantiations. Okay. So that means when you will use net, when you will use registers. Okay. So that time you have to be very careful where you have to use net and where you have to use register. So net is basically used where continuous, that means if you are using net, that means that should be continuously driven. Then only you can use as a net. Okay. But for register, it retains the last value assigned to it. But in net, if you declare any variable as a net, that means it will not retain any last value. Okay. So register will what? It will retain the last value. Means it can store the last value. But in net, it will not store any. Okay. So in register, often used to represent storage element. So basically here the name register means it is not that simple register which you are using for the circuit. Okay. So here the register is basically a data type. So here it can store the last value, and also here basically register we use for a 1-bit storage element. Means not 1 bit, it can store some data. Okay. So however, combination circuit can also be represented using the reg keyword. So we will see some example. In combination also we can use this reg keyword also. In practice, a reg type variable is one that occurs on the left hand side of value assignment statement inside an always block. So we will see what is basically always block and what is assignment statement. That time it will be very clear where you should use the reg and where you should use the net. Okay, here you can see that just one example. Here input A, B, C, D and output wire F. Okay, so here basically this wire F they declared as a net. Okay, because assigned F, that means this should, what happened whenever this will be function, when this function will be occur, that time only this the value will be stored in this F, but it will not remain stored for the long time. When the function will be executed, only you will get the value of a F. Okay. Okay. In arithmetic operation, an integer is treated as a 2's complement signed integer. A reg is treated as a unsigned quantity. That means when you are using some registered data type, in registered data type there are two types. One is reg and another is the integer. The difference is what? In reg, in arithmetic expression, an integer is treated as a 2's complement, but reg is treated as a unsigned quantity. Okay. See, basically what we have seen that there we have a two type of data types. One is a net type, another is a register type. But when you are using net type data type, that time there is a wire, or, one, try, supply 0, supply 1. These are basically a net type of data type. And for the register type of data type are reg and integer. Okay. So for the reg in the arithmetic operation, the integer is treated as a 2's complement signed integer, and reg is treated as a unsigned quantity. Okay. Now the general rule is what? Reg used to model actual hardware registers such as counters, accumulators, and etc. So you will see when you will design that time, basically this reg is used to model the actual hardware. Okay. And integer is used for some loop counting. Okay. Suppose you are writing for a for loop for I equal to this much. So that you have to declare I as a integer. Okay. So it is used like that. So this is one. Now the modeling can be done of a two type. Okay. One is the structural modeling, another is the behavioral modeling. Okay. One is the structural modeling, another is the behavioral modeling. So in structural modeling, basically what do we do? We write completely a structure, means a get. Here the example, the SAR which is given here, you can see this is basically a structural specification. It is not behavioral. Why? Because if you draw the circuit diagram of a full adder, so how you means if you draw the complete full adder circuit, then you will find that some OR gate, NAND gate, XOR gate you have connected. So that the same thing you have declared here. Means the hardware direction, means how you have connected the AND gate, NOT gate, XOR gate, the same thing has been declared in this program. Okay, you can see here that one XOR gate is used where W1 is the output and B is my input. Okay, then another XOR gate has been used where my sum is output and the W1 is coming here and Cin is coming here. Basically, these are actually predefined gate. Okay, these XOR and OR, these are actually all predefined gate is available. Okay, so here only direct, just I will show you. Okay. হ্যাঁ এটার সাইজটা একটু বড় করব কি করে স্যার এইটা ঠিক আছে
control plus
x plus So in behavioral modeling, okay, so this is the basic difference. In structure, here you can see this is a specification of a structural design. Okay, and here you can see this is a behavioral modeling. In behavioral modeling, what we do, we just write the behavior of the circuit. Okay, just behavior means how it will function. Okay, so you don't have to write the complete hardware diagram. We are not defining the complete hardware diagram. Here only we are writing the simply, suppose one example I have shown you, just assign my x f equal to a and b. So I am just assigning, means I am just defining the behavior of that my circuit. Okay, how it will function. But in structural, here what you have to do, you have to complete the circuit diagram, means the logic gates that you have to write here, means you have to code like that the whole circuit. Now here you can see this is a simple counter. Okay, this clock, I've taken one clock, RST, one count. So input I have declared as a clock and RST. Now output you can declare like this. Okay, suppose you want more than one output. Okay, so you can declare 031. That means total 32 bit. This is basically a total 32 bit. You can declare my range total 32 bit. Okay. Now this is called sensitivity list. Sensitivity list is what? When you are writing some always block, this always at the rate percentage of clock. That means whenever there will be some change in the clock, whenever there will be a change in the clock, this function will be executed. Okay. So begin, if RST, then count this, else count will be my incremented. Okay. So this is how you can write the program for the behavioral modeling. Now there are synchronous count, synchronous reset or asynchronous reset that you can see here. For the synchronous reset, that means what? The reset is synchronized with the clock. That means there is no need to define reset separately. Okay. So only what we want, when there will changes in any clock, and you can written here, it is a pause edge of clock. You can write a neg edge of clock if you want to, in a negative edge of your circuit. Okay. If you want that when your clock will fall, that time your circuit will work. So instead of writing pause edge, you can write here neg edge. Okay. And this is a asynchronous type of. That means where here you can see both are defined. In sensitivity list, you have to define both pause edge of a clock or pause edge of reset. That means when either this clock or reset, if anyone is changing, your execution will be start. It will change. Okay. If there is change in clock or there is some change in your reset, then it will function like this. So this is called basically a asynchronous type of. That means your reset and clock is not synchronized. Both are different. So this is how constant values are basically defined. Okay. So for 8-bit binary number, so these are syntax for this one. So for 8-bit binary number, you have to write like this: 8, B, and total 8-bit. B is for each and every bit. Okay. So these for, you can see hexadecimal for H. Okay. So sign number 32. That means if you write simply 25, then it will take sign number of a 32 bit. For logic 0, 1 bit 0, 1 bit 1, logic high. Now there is one more parameter is also can be used in your program. Okay. So parameter you have to declare. Starting off your program, there you can write parameter high equal to 25 and low equal to suppose 5. I have declared some value to this my variable name, high and low. So when you will use high in your program, that time the 25 value will be used. Okay. So this is how you can declare the parameter. Now here in Verilog, basically, or in SDL, these 4 values are used. It is defined. Logic 0 or false, that is 0. Logic 1 or true, that is 1. If there is a cross, that means it is unknown. That is it is a don't care. Okay. And if it is Z, then it is in high impedance state. Okay. So whenever you will write a program and you will simulate, okay, when you will simulate in the waveform, you can see it will show some this value 0, 1, or somewhere it is cross, or somewhere it is Z. Okay. So that means if it is Z, that means it is in high impedance state, and if it is cross, then that means it is unknown, that is don't care. And for 1 it is logic 1, for 0 it is logic 0. So all unconnected nets set to high impedance state. Just remember this one. All unconnected nets, suppose you have declared some net, okay, and you have not used, or you have used some net and you have not given any declaration, it will be in high impedance state. Okay, and all register variable will be set to X. Okay, by default this is. Just I have told you, these primitive gates are already, it is available. Okay. So AND, NAND, OR, NOR, XOR, XNOR, NOT. Okay. This is what? Buffer. Okay. Now here you can see this, it is defined like this, and some UT name. Out means first output, then input, then input. So this is basically a 2 input AND gate. For 2 input AND gate, you have to write like this only, and some name, out, in 1, in 2. If you're using for a 3 input AND gate, then how you will write? And name, out, in 1, in 2, in 3, like this. Okay. If you're using 4 input, then same pattern. You have to write in a same, because this is the basic syntax. Okay. So out, then in 1, in 2, in 3, in 4. Okay. So this way you can use these gates, these logic gates. So you can see using these logic gates in this program, says use these logic gates all. XOR, W1 is output, then A is input, B is input. Same way for AND, W2 is the output, A is input, B is input. Okay. Yeah.
Sir, that means you want me to those do they have any significance on the name?
Which one?
Sir, in the WSTM page, the example that
Which name? This name, U1, U2, U3. No, this name you can give any name.
okay, sir, it won't matter.
It will not matter. Any name you can give. So for all primitive gates, the output port must be connected to a net or wire. Just remember this one. The output port must be connected to a net or wire. That means the output port always you have to declare as a wire type or means net wire type. Okay, the output for the primitive gates. You can see in this example, this output, Cout, sum, and this W1, W2, W3, W4, these are basically what? These are my internal net, and it is has been used as an output only. Here you can see each and every gate, this is W1, W2, W3, W4. All these are output, and that has been declared as a wire. Okay. So this thing you have to remember, means when you're writing a program, this thing you have to be very careful. The output port must be connected to a net, that is the wire type. The input ports may be connected to nets or register type variables. The input can be connected to any net type or register type, but the output you have to connect it to a wire type, net type. Okay. They can have a single output, but any number of input. Isn't it? Just have told you. For 3 input, 4 input, 5 input, 6 input AND gate, just what you have to do, the first will be the output, and again input 1, input 2, input 3, input, like that you can define. So they can have a single output, but any number of inputs. An optional delay may be specified. So whenever, here you can see one more example Sarah has given. Here this is a full adder without delay, and there is another example. This example, it is with delay. So here you can see this delay has been introduced. XOR has 10, output W1, AB is the input. So the delay time of 10 units has been introduced here. Okay. So this input basically, when you are using for a simulation purpose, that time it will be affected. But when it will be synthesized, okay, that time it will not. That means actually when you are going to write your code in some hardware, in some FPGA, that time these delays will be not affected. Okay, so these are used only for the simulation purpose. Yes, you can see Sarah has already mentioned properly specified delays can make the simulation more realistic. That means just for the simulation purpose, just for the checking purpose, you can check. Okay, the specification of delay is optional. Delays are not synthesizable. Okay, so that means meaning that while those can be simulated, a CAD tool does not create any implementation having those delays as specified. That means whatever delay you have specified here, that will be basically not synthesized. Okay, this is only used for the simulation purpose. So logic synthesis tools ignore time delays. Okay, so here the example, and some delays has been introduced. So just we have seen this one, hardware modeling some issue. The values computed can be held in a wire. We have seen the flip-flop or a latch. Okay, some AS trigger storage cell or some level sensitive storage cell. Okay, last time I had, I've told you what was the basic difference between the latch and the flip-flop, isn't it? Latch is basically a level sensitive. Okay, and your flip-flop are basically a age trigger storage cell. A variable in Verilog can be of net data type and register data type. Already we have seen this one. Okay, and here the net data type basically maps to a wire during synthesize. Means when it is synthesized, it is basically maps to a wire, and in register data type maps either to wire or to some storage cell, depending upon the, means it will depend upon your program. Okay, means whether it will create a wire or it will create some storage cell. Okay, that will depend upon your program. Now here there are some block in procedural statement. There are some blocking statement, and okay, that will come later. Here are from the operators. Okay, so when you will write the program, that time you will use all these operators. There are some arithmetic operator, logical operator, some relation operator. Okay, bitwise operator, reduction, shift operation, concatenation. So this operator you will use while writing the. Okay, now the description styles, some styles in the Verilog. There are two different style of description. One is called data flow, and another is the behavioral that we have seen. Okay, one is the data flow. In data flow, basically we have seen all are basically continuous assignment, isn't it? Just I have told you when you're using a net type, that time basically it should be a continuous type. Okay, and for the behavioral, there will be a blocking procedural assignment as well as non-blocking procedural assignment. Okay, there are two types. So for the data flow style, here you can see that I have just identified assign A equal to B and C. Okay, some assign some F of this to C of G. So these are basically what the net being assigned on the left hand side and the expression on the right hand side. The assignment is continuously active. Okay, so when you are doing a data flow style, that means a continuous assignment. That time is, I have told you, basically here you are using a net type, so it will not store any previous data. If you use the range, then only it will store the previous data. But here basically you are using net type, so it will not store any previous data. So it is continuously active. So almost exclusively used to model combinational logic, because in combinational logic you don't require any feedback, isn't it? You don't require any feedback. So that means what? Whatever input you are applying, according to that you will get the output. If input is changes, your output will change. Okay. So that is the combinational logic. But in sequential logic, there will be some feedback path. So for that feedback path, we need some storage unit, some storage cell. Okay. So here the assignment is continuously active and almost used to model for the combinational logic. Okay. So a Verilog module will contain any number of continuous assignment statements. In your module, you can write any number of continuous assignment. Okay, there is no problem. So all of which are evaluated immediately whenever the value of the right-hand expression changes. That means, suppose you have written some expression, assign A equal to some function, then assign B equal to some function, assign C equal to some function. Okay, so that means what? When your first expression will be executed, assign that. Okay, so whatever value will be executed, if you have used that value in your second expression, then after finishing that value will be used in the second function. Okay, so these are basically blocking type of assignment. Okay. So here you can see okay, so the input output were assigned out equal to data of select. That means whenever there will be changes in the select line, it is a simple example of a marks. So for marks, there will be a select line. Suppose for 4:1 marks, how many select line is required? 2 select line. 0 0 S0 S1. So if you change the select line 0 0, your I0 data will come. If you give 0 1, I1 data will be connected. So like that. Okay. So whenever there will be changes in your select input, you will get the output according to that. Okay. Yes.
Can you please explain again, sir, what this third bracket 3:0:0:3 mean?
This one.
Yes, sir.
This is basically where suppose you need a 4-bit bus or 16-bit bus. Okay. So that time you have to declare like this.
Yes, sir. So what is 0? What is 3?
Yes. From 0 to 3. Then that means how many lines? 0, 1, 2, 3. 4-bit. Okay.
Sir, and if it is like 3:0, then
3:0, it's the same thing.
okay.
It's the same thing. So basically what we do, we write the higher byte here and lower byte here, and this is just opposite. Suppose if you're writing 3:0, that means my higher bit will be the S3, S2, S1, S0. Okay. If you're writing 0, these 3, then it will be how much? Your MSB will be S0, S1, S2, S3. Okay. So basically, when you're writing like this, that means this is my MSB and this is my LSB. Okay, for the procedural block, a region of code containing sequential statement, the statement execute in the order they are written. Okay, so they are written. So there are two types of procedural block in Verilog: always block and initial block. Okay, so in the procedural block, a region of code containing sequential statement, there will be some sequential statement, and the statement executed in the order they are written. So there are two types. One is the always block. Always block basically is used for the continuous loop. Okay, the always block we use for the continuous loop. Suppose you want to generate the clock. So for generating the clock means what? You need a always statement, because when your circuit is working, the clock should be present all the times, isn't it? So that means that clock has to be generated full time of your operation of your circuit. So that is why this is, for the clock generation purpose, we use the always block, because this always block is a continuous loop and that never terminates. It will never terminate. And the initial block is executed once at the beginning of the simulation. And this initial block is basically used for writing the test bench. When you will write the test bench, that time this initial block is used. Okay. So because this initial block will only execute it once, means when your program execution will start it, that time the initial part will be executed once, then it will enter your some other part. So this is basically used in the test bench. Okay. A module can contain any number of always block. So you can write any number of always block. In your module, you can write any number of always block, all of which execute concurrently. So this is one special feature. Okay. So suppose you have written 3 always block. So all the 3 always block will be executed at the same time. It is not like that the first always block will be completed, then it will go for the second one. No. For the always block, it is executed concurrently. Means at the same time, it will be executed all the always block. Okay. So a module can contain any number of always block and all of which executed concurrently. Okay. So this is a basic syntax for writing the always block. Always @ this is my event expression. Okay. For clock, we have seen, we have written what? Pause edge of clock or neg edge of clock or pause edge of reset. Means whatever event expression is required, so that you can write here. Okay. Suppose you have used more than, suppose in one big program you have used lots of variable. Okay. Maybe suppose 10 variables are there. So it becomes very difficult to write in all the 10 variables in the event expression. For that time, what we do, we write always @ in bracket a star. So star will define that whenever there will be any changes in your input variable, then it will be always block will be executed. Okay. So if you write the star, that means it is. So begin statement, and this is a sequential statement. The @ event expressions required for both combination and sequential logic description can be used. Only range type variables can be assigned within an always block. So remember, only range type variables can be assigned within an always block. In always block, you have to use only the range type. Why? Because we have seen, because always block is basically a sequential type. And in sequential, we have seen that we need some storage unit. That means some feedback. So that means you require the last value should be what? It should be present. The last value should be present. So that is why it is written. The sequential always block executes only when the event expression triggers. Just I have told you, whenever there will be some changes in the event expression, then this always block will be executed, isn't it? So at other times, the block is doing nothing. That means when there will be no changes in any event expression, your always block will be not executed. It will not do anything. An object being assigned to must therefore remember the last value assigned. Because suppose there was a first time there was some changes in your event expression and the always block has been executed. Okay. Then the result must be present. Why? Because when next time again, if there is any changes in your event expression, that always block should be start from that point only. Okay. So that is why in always block, always a range type of variable is used. So an object being assigned to must therefore remember the last value assigned, so not continuously driven. So only range type variables can be assigned within the always block. So why the range is used always in the always block? So that has been mentioned. Okay. But inside the event expression, you can use any type of, you can use range, where, any type of, but the statement which you are using inside the always block, it should be of a range type. So these are some sequential statement which is used in Verilog. Okay, begin, end, if else statement, case statement. Okay, forever, repeat, while, for loop. Okay, so these are some of the sequential statement which are used in Verilog. So the a time value, we have seen that has time value that makes a block for the time value, time units. So if you given has time here, you can see the time has given how much, and has 8. That means for 8 units it will be suspended, then only it will be executed. So this basically makes a block suspend for this much time value. And for the event expression, makes a block suspend until event expression triggers. So these are basic difference between your these two statement. Means has time value and at the rate event expression. Okay. So this is the basic difference. One will suspend the block for that particular time, and for this at the rate event expression, it will remain suspended unless the next expression is triggered. Okay. So this is the basic difference.
Sir,
Yes.
sir, what does unit define here in
Uh-huh.
terms of seconds? The time unit
Time units.
in terms of seconds.
Oh, that basically you have to define. Okay. So whenever you are writing a program, actually we first of all in your module we define the time. Here you can see this time scale. Okay. So it will work according to that. This is some example of a combinational logic example you can see here. Okay, we are using always loop. We are using always, but it is a combinational logic. Okay, so one example of a module, 2:1 marks, 2 input, select and output F. Okay, so you can see always at the rate star. Just I've told you. Suppose there are many event expression. So without writing all the event expression, we can write the star. Okay. So star means any event expression changes or it triggers. So your always block will be executed. Okay. So always add the star. If select line is 0 or 1, it is 1. Okay. If S, then F. If S equal to 1, then F will be in 1, else F will be in 0. Okay. So this is a combination logic using always. And this is a sequential logic using always. Okay. So these are two examples. This is the one example of a combinational using always, and this is another using always a sequential logic. These are simply DP flop. Okay. Output range Q bar always at the neg edge of clock. So when there will be changes in the clock in the negative edge, it will begin Q equal to D or it will be Q equal to D bar. Okay. Now here you can see I will yes, a blocking and non-blocking assignment. Okay, so in procedural statement we have seen there are two types of it. I've told you one is the blocking, another is a non-blocking assignment. Okay, so a sequential statement within procedural block always and initial can use two types of assignment. One is a blocking assignment. For blocking assignment we use this type of operator, and for the non-blocking assignment we use this type of operator. Okay. So for blocking assignment, most commonly used type, the target of assignment gets updated before the next sequential statement in the procedural block is executed. A statement using blocking assignment blocks the execution of the statement following it until it gets completed. Okay. So in blocking assignment, I have told you, unless and until the first assignment is completed, execution is completed, it will not go to the second one. Okay. So in blocking statement, a statement using blocking assignment blocks the execution of the statement following it until it gets completed. Recommended style for modeling combination logic. So this type basically we use in a combination logic type for modeling. Okay. So there we use a blocking type of assignment. But in non-blocking assignment, you can see the assignment to the target gets scheduled for the end of the simulation cycle. That means what? Normally occurs at the end of the sequential block. Statements subsequent to the instruction under consideration are not blocked by the assignment. Okay. So that means if there are 2-3 execution is there, so it will not stop the previous execution, or it will not stop the next execution. Okay, so it will use basically for the sequential logic and can be used to assign several reg type variable synchronously or some clock. So this is the main basic difference that normally occurs at the end of the sequential block, and statements subsequent to the instruction under consideration are not blocked by the assignment. Okay. And there are some rules to be followed. Okay, Verilog synthesizer ignores the delay specified that already we have discussed. That delay specified is not basically synthesized. Okay, it is used for the only your simulation purpose. A variable cannot appear as the target of both a blocking and non-blocking assignment. That means a single variable, okay, a same variable you cannot use for the blocking and non-blocking statement. Okay. So here, like this, value equal to value plus 1 and value is equal to this one. You cannot use this way. Okay. Because both are, one is blocking statement, another is the unblocking statement. Okay. So a variable cannot appear as the target of both a blocking and non-blocking statement. Target means what? The output. Okay. Here both are using output, na? Value is the output. That is equal to value plus 1, and the value is also some output here. So both the target you cannot use in a same assignment. So here's some example. This one for the synchronized up-down counter, a module, then module name, and these are all your variable input declaration, output declaration, and this is your always block. Okay, so this means you have to follow this syntax. Now writing program means basically when you're writing the structural type of, that time the whole complete circuit diagram, that only you have to just define in your program. Okay. So sir has given you some example. Just I have already discussed this one. This is for a full adder. Okay. In a structural specification, this is also a 4-bit ripple carry adder. Okay. This is also in structural specification. You can see inside this module. This is my module, isn't it? This is my module. Ripple 4-bit ripple carry adder. In this module, these are all my instantiation. This full adder. That means what? This full adder structure is already defined in some module. These are basically instantiation. Okay. So this is my main module. Okay. So this is my full adder structure module. And now this module I have instantiated here 4 times. Okay. Suppose what we do when you are writing the program for the suppose 4-bit ripple carry adder. That is what? First of all, I will write 1 bit adder, full adder. Okay. That I will call 4 times. So in C, what we do, we just call the function here. But here it is not like that. Here inside the module, you have to insert. That means actual hardware is going there. If you draw the diagram, what you will find? That there are completely 4 full adder is present. So that same thing is done here only. Okay. So that means here you have to, it can be instantiated. Okay. Instantiated means 4 full adder has been placed. So these are structural specification of a D flip-flop. Okay, same way. Okay, here all the gates has been used. Predefined NAND gate. Okay. Now we will come to the main thing. Just I have shown you the parameter has been used here. So lots of examples you will find. Okay. Loops already I have discussed. It use while loop, for loop, forever loop, repeat loop. Okay, so all these are used. Memory can also be you can done here. Okay, now test bench. So whatever module you have written for testing that, you have to write the test bench. Okay, so what is basically a test bench? A Verilog procedural block which executes only once, used for the simulation. Test bench generates clock, reset, and the required test vector. So that means this is a basic block diagram. So this is the test bench. This is your module under test, means the module which you are going to test. That means from here you will send the stimulus, and whatever output you are getting from that your circuit, that has been compared with your logic. Okay, so this is basically a test bench. That means the module means when you are writing some module. So for testing the module, you have to write the test bench, and that you have to test. So how to write the test bench? Create a dummy template, declare inputs to the module under test. Okay, module under test, that is what? As range, and the output as wire, and instantiate the MUT. That means this module under test. Now initialization, assign some known value to the MUT inputs. Okay, that means the module which under test you are using. The clock generation logic, various ways to, and may include several simulator directives. That means this dollar display, dollar monitor, dump file, dollar dump verse, or dollar finish. These are basically used to your verify the your circuit analysis. Okay, this has been used. We will see one example, then only you can understand. Okay, but dollar display, dollar monitor, dollar finish. Okay, so these are used. So I will show you some example. So this is my simple example. Okay, a module, TST AND gate. Just I'm testing the AND gate. That is my out. AB is my input. Input I have declared AB. Output out. I have assigned this one in module. Okay. Now to test this module, to test the module, you have to write the test bench. So here you can see, just we have written the test bench. Okay. And I have I have this one input reg A, reg B. Okay. Now when the just you can see here A and B I have declared as my input here. Okay. Whatever input you will declare here as a input, that you have to declare in test bench as a reg. Okay. And output as a wire. So initial begin. Now these two files, this dump file and dump var, these two, when you're testing your circuit in iVerilog. Okay. So just to for the simulation purpose, we will use their GTK wave. Okay. So for using GTK wave, what you have to do? You have to store the means the file should be in .vcd format. Okay. So that is why here we are writing a dump file whereby this TST and module will be stored in .vcd format, and this dump variable means what? Whatever changes will be in the variable, that will be dumped in my that file. Okay. So these two instruction always you have to write if you are using your GTK wave to simulate your module. Okay. So these two you have to use always. Now I have assigned some value. I have just initialized some input A equal to 0, B equal to 0. Now you can see I have written one another statement, dollar monitor, dollar time, this format. Okay, syntax. This is the syntax. Already we have seen here for this one, dollar display, dollar monitor. Okay, these statements are there. Syntax are there, dollar monitor. Okay, dollar monitor is what? Similar to dollar display, but prints the value whenever the value of some variable in the given list changes. That means if there is any changes in the list, it will be displayed. Okay, and dollar display will what? It's print text or variable to the output. Okay, this statement, and I have given some input a equal to 0, b equal to 0. I have given some delay, #1 delay, #1 delay of this. I have changes my input variable, a equal to 0 0 initialize, then 0 1 1 0 1 1. Okay, so I have used your dollar monitor and dollar finish. End for this initial begin and end module for this module. Okay, so this is my test bench. So to execute this program in iVerilog and also in GTK Web, so first of all, you have to write this statement, iVerilog. Okay, this is basically -o means output, isn't it? It is for the output file. TST and is my output file. Okay, and this you can see this is the actual syntax, isn't it? In while in Icarus Verilog, we have seen to execute the iVerilog. This is the actual syntax. iVerilog -o, my out.out is my output file, and this is to my input file. Okay, but if suppose there is 10 input file, okay, that time it becomes very difficult to write all the 10 input file. So for that, what you can do, you can create one txt file. So this is, I have created one txt file, and inside a txt file I have written all my module. Okay, here I have used only 2 modules, so I have written tst n.v and tst_testbench.v. Okay, so what happens when you will execute the program, that time instead of writing this whole statement, there's this way, tst and tb testbench.v and tst_n.v, you can simply write that text file. This way you can write iVerilog, this tst end -c tst_n.txt. Okay, then it will means how many modules you have written inside your txt file, all the modules will be executed one by one. Okay, now using vpp command, you have to execute that one, your tst and dot, that is basically which file? Okay, so here you can see you are getting for each and every time, for time equal to 0, I have given my input a equal to 0, b equal to 0, the out I am getting 0. For time 1, a equal to 0, b equal to 1, output I am getting 0. This is an AND function, you can see. So this is coming due to why? Because due to that dollar monitor function, which I have written the dollar monitor. This dollar monitor, this due to this dollar monitor, you are getting this output. Okay. Now, if you want to see the waveform, so you have to execute GTK wave. Okay. So tst and testbench.vcd. So whatever name I have given in test bench, you can see here I have given name tst and _tb.vcd. So this file you have to execute. Okay. So if I execute this one, so your GTK wave will be opened. Okay. Now here you can see you cannot see any waveform here. So for that you have to just expand this one. You click this one. Now you can see all the type of signals which have been used. Now only you have to drag and drop here inside this signal. So this is my wire A, wire B, and this is my wire out. Okay. So now you can see the waveform. Okay. Last check. Okay. So you can see A equal to 0, B equal to 0 for each and every clock. For my A, by changing the A and B input, you can check the waveform like this. Okay. Also here you can change the color of your data format. You can change the color. I can make this as my suppose blue. Okay. So this I can change to some other color. Some yellow. So you can change the color of your. You can change the color also to see the waveform. Okay. So now suppose what happened. You have checked some status. Okay, of your waveform. Now you find some fault. So then what do? You have to change the program. So after, if you go out from here and if you change the program, what will happen? The previous whatever you have checked here, it will be erased. So for that, what you can do, you can save this file also. Okay. So with this, you can save. Go to the file and write save file as, and give some name with the extension .gtkw. Okay. So this way also you can save your GTK wave file also. So once the file has been saved, if you want to open the save file, then you just simply you have to write GTK wave txt.db.vcd, and you have to give the file name what you have config. Suppose I have given the file name config. If I have given config .gtkw. Okay. So if you execute this one, then whatever you have left in the last waveform, that you can check. Okay. So basically, this we have discussed in very short. Okay, because Verilog is a very vast. Just I have discussed you the just key points. Just to write the Verilog, how to write the Verilog program, and how the means what are the syntax, and how to write the test bench. Okay. Now this needs a basic practice. More and more program you will write, it will be clear. Okay. So the sir which has given to you the program for your assignment. So you carry on with your assignment. Okay. So already I've already installed in this machine. Okay. So you can write the program and you can check.